Hello everyone. In today's lecture, I am going to explain the fragmentation pattern in alkane and alkene. For the study of fragmentation pattern in different classes of organic compounds, it is necessary to understand the rules of fragmentation. So, let's begin with the rules of fragmentation. Already in previous lecture, we have studied the rules of fragmentation. Now, let us see in brief. First of all, what is fragmentation? Fragmentation is nothing but the cleavage of bonds. So, in the fragmentation process, cleavage of bonds like carbon-carbon single bond or carbon-hydrogen or carbon-nitrogen bond occurs. So, first important rule for the fragmentation or for the cleavage is that the compounds with same class has a unique fragmentation patterns and used as fingerprint for qualitative identification. Suppose we consider here the cleavage or the fragmentation for these two examples. Here the cleavage occurs at this carbon carbon single bond, and again here the cleavage occurs. So cleavage occurs at alkyl substituted carbon at branching point. Why it is so? To give the more stable carbocation. Cleavage occurs at alkyl substituted carbon at the branching point to give more stable carbocation. As we know, tertiary carbocation is more stable than secondary, than primary, than methyl carbocation. Suppose we have the example of butane and pentane. So in this, the fragmentation occurs and we get the number of peaks, but the peaks are separated by 14 mass unit. Then the fragments like double bonds, arene and allylic cations, it also resists the fragmentation. Then if we consider the even electron rule, even electron species will not fragment into two odd electron species but fragments into cation and neutral molecule. So that is called as a even electron rule. Then in the fragmentation, frequently neutral fragments which are more stable such as CO, C2H2, H2O, NH3, H2S are lost. More stable neutral fragments that will be removed during the fragmentation as carbon monoxide, ethene, water, ammonia, hydrogen sulfide, like that. Next important rule, that is Stevenson rule. According to Stevenson rule, fragmentation occurs in such a way that positive charge resides on fragment with low ionization potential, generally on small fragments. So on the small fragment, the positive charge present on small fragment and the larger fragment acquires a radical. So it is called as a Stevenson rule. We know that a fragmentation process occurs through either by homolytic or heterolytic cleavage, but there is cleavage of bond. And if the fragmentation occurs, then we get radical and cation. So during the fragmentation, according to Stevenson rule, the fragmentation occurs in such a way that positive charge resides on fragment with low ionization potential and that having a small fragment present with positive charge and larger fragment with a radical. So that is the Stevenson rule. Next important rule, that is nitrogen rule. So according to this, compounds with even number of nitrogen or lacking nitrogen give molecular ion peak at even mass to charge value and vice versa. That means the compound with odd number of nitrogen give molecular ion peak at odd mass to charge value, and the compound with even number of nitrogen or lacking nitrogen give molecular ion peak at even mass to charge value. So this can be explained by taking some examples like this. Here the compound C2H2, there is no nitrogen, having mass to charge value 26. Second example, methylamine CH3NH2, having one nitrogen, mass to charge value 31. And third example, phenylhydrazine C6H5NH2, having two nitrogens, mass to charge value 108. When we look here, mass to charge values, then for no nitrogen or the compound lacking nitrogen, it shows the mass to charge value even. Whereas the compound having one nitrogen, that is odd number of nitrogen, mass to charge value is also odd number, and the peak is observed at odd mass to charge value, M to Z value. And the next example here, even number of nitrogen, two nitrogens, hence mass to charge value M to Z ratio is 108. So the compounds having even number of nitrogen or lacking nitrogen gives the molecular ion peak at M to Z ratio, that is also even. These rules are useful to study the fragmentation pattern in different class of organic compound. Now let us see the fragmentation pattern in alkanes. So what are the different characteristics observed in the fragmentation pattern of alkane? Let us see. So these are few characteristics of fragmentation. First important, fragmentation in alkane occurs at every carbon-carbon single bonds, and it gives the cluster of peak separated by 14 mass units. So when the fragmentation in alkane occurs, each and every carbon-carbon single bond is going to cleave. Therefore, as there is a formation of cluster of peaks and each peak is separated by 14 mass units. So we get the cluster of peaks due to the cleavage of every carbon-carbon single bonds in the alkane. The second important one, the molecular ion peak appears at mass to charge value is equal to CnH2n plus 2 is equal to 14n plus 2, where n is nothing but number of carbons. So depending upon the number of carbon atoms, we get the molecular ion peak at M to Z is equal to CnH2n plus 2, or that is equal to 14n plus 2. Third important rule, if you observe the branch chain alkane, in the branch chain alkane, the fragmentation occurs and it gives less intense molecular ion peak than straight chain alkane. Branch chain alkane gives less intense peak than straight chain alkane. We know that the cleavage occurs at the branching point or also at the alkyl substituted carbon atom. So, in branch chain alkane, cleavage occurs readily than straight chain alkane, and when the cleavage occurs, it gives the stable carbocation. Therefore, the molecular ion of branch chain alkane is converted to stable carbocation very fast. Therefore, the molecular ion in case of branch chain alkane is less stable as compared to straight chain alkane. And the stability of molecular ion in the branch chain alkane is less stable, so the intensity of molecular ion is less as compared to straight chain alkanes. So the branch chain alkane gives less intense molecular ion peak than straight chain alkane because the fragmentation of molecular ion peak occurs readily to form stable carbocation in branched alkane. As the stability of molecular ion in branch chain alkane is less stable, so intensity of molecular ion peak is less as compared to straight chain alkanes. Next one, the fragmentation gives mixture of radicals and carbocations. The positive charge resides on smaller fragments. Already we have studied that rule called as Stevenson rule. So the fragmentation, it gives the mixture of radicals and carbocations where the positive charge reside on the smaller fragments and the larger fragment will acquire a radical. Then the propyl and butyl ions are most abundant, so they appear as base peak. So base peak is observed in alkane at mass to charge ratio 43 or mass to charge ratio 57. That is at M to Z 43 or M by Z 57. Base peak is observed in alkane at propyl or at the butyl ions which are most abundant M2Z43 or M2Z57. Now let us see the example, the fragmentation pattern in alkane. So this one is the example here. In this example, the fragmentation occurs as the first important characteristic. Fragmentation of alkane occurs in such a way that there is a cleavage of each and every carbon-carbon single bonds. And due to that, it gives a cluster of peak. Each peak is separated by 14 mass unit. So here, each and every carbon-carbon single bond is going to cleave. Therefore, as there are 5 carbon-carbon single bonds, so the cleavage occurs by using 5 different ways. So we can fragment this molecule in 5 different ways. So it is the hexane, straight chain alkane, hexane, and we get the cleavage by 5 different ways. Each and every carbon-carbon single bond is going to cleave so that we get the number of fragments. So let us see one by one. So the first step, the hexane on ionization gives the molecular ion peak at M to Z is equal to 86. So first ionization occurs and we get peak M by Z is equal to at 86. Now the first step, the fragmentation here at this carbon-carbon single bond, the cleavage of carbon-carbon single bond, and due to that we get the formation of this fragment. So CH3 CH2 thrice CH2 radical plus CH3. So M by Z is equal to 15. So we will get the formation of methyl cation, first fragment which is observed. So according to Stevenson rule, the positive charge resides on smaller fragment and the radical reside on the larger fragment. So first of all, there is a formation of methyl cation. So if we represent here, that is the A, cleavage A, carbon-carbon single bond, first cleavage. Now the next one, that is formation of ethyl cation. So here the cleavage occurs at this bond, carbon-carbon single bond. So due to that, there is a formation of these two fragments. So one is again smaller fragment acquires the positive charge according to Stevenson rule. So CH2 CH3 plus, that is a ethyl cation having M by Z is equal to 29. So peak is observed at this fragment M by Z 29. Next one, here the cleavage occurs at this carbon atom. So carbon-carbon single bond represented by C, cleavage. So due to that, there is a formation of a fragment which is a one fragment having the positive charge and another fragment having a radical. So if we observe in the hexane, there is a symmetrical cleavage at the C point. So here the symmetrical cleavage occurs. One fragment acquires positive charge and another fragment acquires radical. So the peak is observed at M by Z 43. So we'll get the formation of propyl cation. Now next one, again the fragmentation occurs and the cleavage of the bond carbon-carbon single bond. So we can represent this point D cleavage. So we'll get the formation of butyl cation. There is a formation of butyl cation having M by Z is equal to 57 and the radical is present on the smaller fragment. Next one, last one. Here again the cleavage occurs and due to that cleavage there is a formation of two fragments. Now here the larger fragment acquire the positive charge, so that peak is observed at M divided by Z is equal to 71. So M by Z is equal to 71. This fragment is nothing but pentyl cation, formation of pentyl cation and methyl radical. So in the hexane, that is the alkane, in this the fragmentation occurs. Each and every carbon-carbon single bond is going to cleave, so that 5 bonds are cleaved by 5 different ways and give the number of fragments. So the fragmentation occurs and so that the peaks are observed at M by Z 15, M by Z 29, M by Z 43, M by Z 57 and M by Z at 71. So all these peaks are separated by 14 mass units. So let's see the mass spectrum of hexane. So this one is the mass spectrum of N-hexane. As already we have studied the fragmentation observed in the N-hexane, formation of methyl cation, ethyl cation, propyl cation, butyl cation, pentyl cation, etc. So first peak observed, that is molecular ion peak at M by Z 86. So molecular ion peak M plus peak is observed at 86. Then base peak, most abundant peak at M by Z 57. Another peaks which are observed at number of fragments, like peak at M by Z 15, then at 29, at 43, and each peak is separated by 14 mass units. Again, there are another fragments which may be formed due to the loss of hydrogen, and due to the loss of hydrogen that gives the peak at M by Z 85, 55 and 41 and also at 27. So it is the mass spectrum of N-hexane. So we should remember that is a molecular ion peak, that is a base peak. Cluster of peaks are observed due to the cleavage of carbon-carbon single bond in N-hexane, that is a straight chain alkane. So the cleavage occurs at the number of carbon atoms, carbon-carbon single bonds, and due to that the peaks or the cluster of peaks are observed. Now let us see the next example, that is branch chain alkane. So here the fragmentation in branch chain alkane. Let us see the example isobutane. Here again first step is the ionization. So isobutane undergo the ionization and that give the formation of a molecular ion peak at M by Z 58. Further, there is a loss of H radical. Again, there is a formation of that peak M by Z 57. So there is a formation of such a type of the cation, positive charge species. So peak is observed at 57. Next step is that, as we know, that the cleavage occurs at the branching point or at the alkyl substituted carbon atom. So cleavage occurs here, so that there is a formation of CH3 plus, that is positive charge resides on the smaller fragment. So the smaller fragment having the M2Z value 15, and there is a loss of C3H7 radical. Or also the second possibility, there is a loss of CH3 radical and the peak is observed at M by Z 43. So these are the two fragments observed. So we know that the cleavage occurs at the branching point or at alkyl substituted carbon atom. So in the branch chain alkane, the cleavage occurs readily than the straight chain alkane. When the cleavage occurs, it gives the stable carbocation. Therefore, molecular ion of the branch chain alkane is converted to stable carbocation, and the intensity of the molecular ion is less as compared to straight chain alkanes. Now let us see the mass spectrum of the branch alkane, that is isobutane. So during the fragmentation, most stable carbocation is formed and we get the peak at M by Z 15 and also at 43. So we get the peaks due to the cleavage of carbon hydrogen bond and due to the cleavage of carbon-carbon single bond. So here there is the cleavage of carbon-carbon single bond, formation of methyl cation, and in the second case there is a cleavage and there is a loss of CH3 radical. So the peak is observed at M by Z 43. Now the next one, that is fragmentation pattern in alkene. So let us see first of all the characteristics of fragmentation in alkene. So first important thing, in case of alkene, the fragmentation occurs and due to that more intense molecular ion peak is observed as compared to alkanes. Then the fragmentation, it occurs by allylic cleavage and by vinylic cleavages. The positive charge again remain on the fragment having the double bond. Here the positive charge is present on the fragment which is having the double bond. And allylic cleavage, why it is more preferable in the fragmentation of alkene, because the allylic cleavage give the resonance stabilized allylic carbocation and hence it is more favored, whereas the vinylic cleavage is least favored. Then the carbon and hydrogen rearrangement are observed, hence the isomeric alkenes cannot be distinguished during the fragmentation. And if you observe the example, that is terminal alkene give the characteristics peak at M by Z 41 due to allylic carbocation. And the allylic cleavage, it is more preferable because of resonance stabilization, and due to the resonance stabilization there is a formation of allylic carbocation which is more stable. So let us see the example of 1-butene. 1-butene is a terminal alkene. As we know that there is the characteristics of the terminal alkene which give the peak at M by Z 41 due to allylic carbocation. So 1-butene, first step, undergo the ionization. There is a formation of molecular ion and the peak is observed at 56. So first of all, ionization, formation of molecular ion peak M by Z 56. Then vinylic cleavage, if you observe the vinylic cleavage, there is a loss of C2H5 radical and we get the formation of vinylic cation at M by Z 27. And if you consider the allylic cleavage, there is a loss of CH3 radical and there is formation of allylic cation. So this allylic cation can be observed at M to Z 41, and if you observe the resonance stabilization, it is more stable. Allylic cation is more stable, and that terminal carbon-carbon single bond, terminal carbon-carbon single bond shows the cleavage through homolytic cleavage and there is a formation of allylic cation which is more stable. When we observe the vinylic cleavage, It also occurs by homolytic cleavage, but it is less stable as compared to allylic cation, because allylic cation, it will be undergo the resonance stabilization and forms the most stable carbocation. So the fragmentation in 1-butene, when we observe, it ionizes to form molecular ion with M2Z56. Then the molecular ion fragments via vinylic cleavage to give the unstable vinylic cation with M2Z27, and also the molecular ion fragment give the allylic cleavage to give the resonance stabilized allylic cation with M2Z41. So the peaks are observed at M by Z 56, mass to charge ratio 27 and mass to charge ratio 41. So the peaks are observed at these M to Z values. Now let us see the spectrum of 1-butene. So we should remember the molecular ion peak in case of alkene is more intense as compared to alkane, and here the fragmentation occurs by allylic cleavage and vinylic cleavage, but allylic cleavage is more stable than the vinylic cleavage due to the resonance stabilization, and carbon and hydrogen rearrangement are also observed, hence isomeric alkenes cannot be distinguished. Terminal alkenes having the characteristics to show the peak at M to Z value 41 due to allylic carbocation. Let us see the spectrum. So it is the mass spectrum of 1-butene. It is a terminal alkene having the characteristic peak at 41. So base peak is observed at 41 and molecular ion peak at 56. Molecular ion peak is observed at 56. As we know, the tallest peak is called as a base peak. So it is a base peak, and if the height is more, that means in sample and also in nature it is present in more amount. So tallest peak is obtained, and that is also called as a base peak. So height and intensity is also greater. So here in case of terminal alkene 1-butene having the base peak at M to Z 41. So that is the interpretation of the spectrum of terminal alkene 1-butene. Now let us see the fragmentation pattern in alkene having gamma hydrogen. So what happens if the gamma hydrogen is present in alkene? So let us see the example. So alkenes having gamma hydrogen rearrangement in which gamma hydrogen is transferred from gamma carbon to carbon having a radical. Two bonds are cleaved with the formation of McLafferty ion and alkene molecule. So if the gamma hydrogen is present, there is a rearrangement occurs in which gamma hydrogen is transferred from gamma carbon to carbon having radical. So two bonds are cleaved with the formation of McLafferty ion. So here if we consider first step, again the ionization to give the molecular ion. So here the molecular ion peak is observed at M to Z 98, mass to charge value is 98. So the gamma hydrogen, if we locate here, the gamma hydrogen is transferred from gamma carbon to carbon having a radical. So from this position it is transferred to the carbon having the radical, and so that two bonds are cleaved with the formation of McLafferty ion and the alkene molecule. So McLafferty ion, again it shows the peak at mass to charge value 56. So there is a formation of such a type of the McLafferty ion and the alkene due to the cleavage, and first step is nothing but the transfer of gamma hydrogen from gamma carbon to carbon having radical. So there is the two bonds cleavage and formation of McLafferty ion and the alkene molecule. So it will be observed in such alkenes having gamma hydrogen. So in today's lecture, we have discussed the fragmentation pattern in case of alkane and alkene with example. Also, we have studied the mass spectrum and interpretation of mass spectrum of alkane and alkene. In next lecture, we will see the fragmentation pattern of different functional groups. Thank you.